This is going to be sections 9.7 and 9.8. I'm going to cover them together as one section because they both have to do with complex numbers, and they are just introduction to complex numbers as well as adding, subtracting, multiplying, dividing complex numbers as well. So they kind of all go nicely as just kind of one section on complex numbers. So these complex numbers are a result of what happens when you take the square root or any even root, like a fourth root, sixth root, of a negative number. So previously we said that the square root of negative 25 had no real number solution. That's because it has what's called complex or imaginary numbers as a solution. So when I say complex and imaginary, those are synonymous. So for definition, we define the square root of negative 1 as being the imaginary unit I. That way, if you square I, you know if you square a square root, it gets rid of the root, right? So I squared then is defined as being negative 1. So, here's what we get. The square root of negative 25 can be thought of as the square root of negative 1 times 25. The square root of negative 1 is what we're calling I, the imaginary unit, and the square root of 25 is 5. So we get that the square root of negative 25 is 5i. Now, what that means is that if you've got a negative under a square root, that it comes out from under the square root into the form of an I. Your calculator will not do this. Okay, it does not do imaginary numbers. So we're kind of on our own here. All right, so let's simplify this. So the square root of negative 49, we can take that negative out as the square root of negative 1, which becomes I. And then the square root of 49, well, we know what that is. That's just 7. So my answer ends up being 7i. You can write I7. It's just usual, more common notation to put the number first, just like 7x, you wouldn't put x7. So it's just kind of more standard notation to put the number before the letter. Now, you can skip all this in between stuff and just say, hey, I see that negative, I see you under that radical, and whoop, that's just going to come out as an I. And then you just handle the square root of 49 as usual. So the square root of negative 4, you can do all this in between stuff, or you can just say, hey, I see that negative. It's going to be an I. Square root of 4 is 2. Boom, right? The square root of negative 1, well, that's just I by definition. You could put a 1i right here, but you know how Hawk says about those unnecessary ones, so you don't want to put that unnecessary 1 there. So what about something that's not a perfect square, like say the square root of negative 90? Well, that negative is going to come out as an I. And then the square root of 90 is going to be the same as the square root of 9 times the square root of 10, which is 3 root 10. You can use your calculator for that one. So we can do the square root of 90 and get 3 root 10. So you can still use your calculator for the square root of 90 part of it, to simplify that part. You just have to see that negative and just know that that's going to be is going to come out from under that radical in the form of an I. Okay, so imaginary numbers, also called complex numbers. Complex numbers are kind of weird because they have this standard form of a plus bi. Now, that's not two complex numbers. That's one complex number. It just happens to have two parts to it. Okay, so it's weird because it looks like it's two numbers being added together, but it's not two separate numbers. It's one complex number, and that complex number happens to have a real part and an imaginary part. So in a complex number or an imaginary number, whichever one you want to call it, this number is what we call the real part, and this number is what we call the imaginary part. How can you tell the difference? Well, the imaginary part is the one hanging out over here with the I. The real part is the one over here by itself. Now this can be a plus or a minus. It doesn't have to be a plus. You know, if b happens to be a negative number, then we could write it as subtraction. All right, so let's identify the real and the imaginary parts for the following complex numbers. So Hogs is going to ask you, give you, two little boxes for you to put those answers in. And this really is super duper simple, okay, if you know where to look. So in the number 2 plus 3i, the real part, 2. The imaginary part, the coefficient of I here, is positive 3. You don't have to write the plus. 5 minus 2i. 5 is the real part, minus 2 is the imaginary part. Now, does that mean that the first number is always the real part and the second number is always imaginary? Not always. It just usually happens that they're written in that form, but in this case, 7i, that's the same thing as 0 plus 7i. 7 is that coefficient of I, so it's your imaginary part. There is no real part to this, so we say that's 0. If you happen to have a number like, say, 8 that doesn't have an imaginary part, well, then you can think of it, there's my little happy little thought cloud here, as 8 plus 0i, in which case its real part is 8 and its imaginary part is 0. All right, if it seems like I'm moving a little fast, remember you do have a pause button, so you can always pause these. This one's going to be a fraction, so I can split this up into 5 halves and then minus I over 2. That coefficient of I is an understood 1 right here. So I pulled this apart into 5 halves minus 1/2 I, so that you could see that the real part is 5 halves, the imaginary part's negative 1/2. Be careful, because I could see you maybe accidentally saying, oh, the real part's 5 and the imaginary part's negative 1. What do I do with this 2? Well, I'm just going to ignore it. Can't really do that. All right, we add and subtract complex numbers just like we did with polynomials, just like we did with the radicals. We just combine like terms. Okay, so let's say we wanted to add 6 plus 2i plus 4 minus 7i. We just add the like terms. You add the real parts together, 6 plus 4, and then you add the imaginary parts. This is seriously no different than if there was an x there. So that's a plus 2i minus 7i. So combining those coefficients, 2 minus 7, we get that minus 5i. These are not like terms, so you can't combine those. All right, if we had subtraction, then I need to distribute that minus to both of these, in which case I would get 8 plus I, and then minus 3 plus 2i. Combining like terms, 8 minus 3 is 5. That's a 1i right there, plus 2i. So that's going to give me a 3i. All right, what if I have addition and subtraction together? Well, the addition, not a big deal. The subtraction, again, I'm going to have to distribute because I'm subtracting that entire quantity. So distributing that out and then combining the like terms that we get. So I kind of underlined all those real parts once to combine those, and the imaginary parts, I underlined those twice to show that those were all like terms. And then that's how I combined those. So adding and subtracting just like polynomials, just like if there was an x in there, okay? So what happens if we bring in some radicals? All right, well, kind of some of the same stuff, right? We know how to do like terms with radicals. That's a subtraction, so I am going to distribute that out. So we get those like terms of minus 8 and minus 2 to be minus 10. These two, look at this. You can't really combine that root 6 and that 7, or sorry, that minus root 6 and that minus 7. But what you can do is factor out that I. See how that's a minus right there? If you factor out that I, you're going to be left with root 6 plus 7. So factoring out, remember, is the opposite of distributing. So if I redistribute this, I would get minus I root 6, and then minus I times 7. Hawks prefers you to give exact answers. If you try to write this as a decimal, it's not going to like that. So I just put a little side note there about how I got this by factoring out the I and the negative. All right, next up, these do not have I's in them yet. Oh, but soon. Okay, so I'm going to rewrite this square root of 49 as 7i, right? Because the square root of 49 is 7. That square root of that negative 1 is I. The square root of 81 is 9. That negative under that square root becomes an I. All right, we're subtracting, so I'm going to distribute that out. And then I'm just going to combine those like terms. These are not like terms, so don't try to combine those together. Okay, so that's the end of 9.7. Now 9.8, so that ends 9.7. 9.8, we go right into multiplying. So we just did addition, subtraction. Now we're going to do multiplication of complex numbers. Very similar to what we did with polynomials. The difference is we have to replace I squared with negative 1 because that's what it's defined as being. All right, so let's see how that plays out. If we're going to multiply, say negative 3 times the quantity 2 minus 7i, we're going to distribute. So I just kind of showed you how that minus 3 got distributed. That simplifies to be minus 6. And then that's a minus from the subtraction. So minus from that subtraction, and then that negative. So those two are going to make a positive. If you skip this middle step and you just say, hey, I know that negative times that negative is going to give me a positive 21i, that's awesome. You can totally skip steps. That's great if you can. All right, what happens if I have a 5i that I need to multiply? Well, 5i times minus 4, and then 5i times 6i. Multiplying these pairs, so multiplying those together and those together. This first pair gives me minus 20i. This one gives me 6 times 5, which is 30, and then I times I is I squared. Now notice I've color-coded this. Every time I see an I squared, I'm going to do it, I'm going to, accent it in blue so that you can see I'm going to replace it with the number negative 1. If I is defined as the square root of negative 1, then we define I squared as being negative 1. Now what that does is those multiply together to give me minus 30. Now you can write this either way. If you wanted to write the real part first and then the imaginary part, or imaginary then real, it does not matter, even in Hawks. Okay, let's keep on multiplying. So here, if I'm going to distribute this I root 5, so I distributed the I root 5, and let's see how these clean up here. This 7 is not part of the radical, so it's going to go in front of the radical. These two, when you multiply it, you get I times I, which is I squared. And then these two are both under the radical, so that's going to combine to be a root 15. The I squared simplifies to be a negative 1, and that minus times that negative changes that to a positive. Okay, so there's your final answer. All right, this one is going to be a binomial times a binomial, so it's going to be similar to FOIL. You do have to use the distributed process here. So multiplying all this out, we get 3 times 2, which is 6. 3 times minus 4i is minus 12i. 5i times 2 is 10i. 5i times minus 4i is 20i squared. See, it's in blue again. Every time there's an I squared, I'm going to change it to minus 1. This is well, I shouldn't say no different, slightly different than if there were an x here. All right. The only difference is instead of having x squared in your answer, we have I squared, which simplifies to be minus 1. So if you multiply those two together, you're going to get a positive 20. And then if you add the 6 and the 20, those like terms, you get 26 minus 2i. All right, next up here. If you have a quantity squared, remember that's that thing times itself. Do not try to distribute that squared. I know it's tempting, all right? I know it. I know you guys love the distributed property. You want to run off to Vegas and get drunk and marry it because you just love it so much. Do not distribute a squared. You cannot do it. You have to rewrite this thing twice and then distribute out. So distributing all that out, we get this. These middle terms are like terms. I can combine those. I'm going to replace that I squared with a minus 1. So that positive 49 times a minus 1 changes that to a minus 49. And then these two outer ones are like terms. And those combine to be a minus 24, and that 70i comes down. Okey-dokey. Let's talk about exponents on I. When we talk about the powers of I know this looks like a whole bunch of mess, right? It's just like a whole bunch of ones and i's and stuff. We have I. I squared is defined as being negative 1. I cubed is negative I. Because it's I times I squared is negative 1, so you get negative I. I to the fourth is just I squared times I squared. Negative 1 times negative 1 is positive 1. I to the fifth is the same thing as I to the first. Because it's I times I to the fourth. I to the fourth is 1. Now, here, look at what happens. We have this cycle that happens, right? We have I, negative 1, negative I, 1. I, negative 1, negative I, 1. So we end up with this cycle that happens where every multiple of 4 for that exponent, we get 1. So we come out with this kind of nifty thing that I to the n is equal to 1 if n is a multiple of 4. So I to the fourth, I to the 8th, I to the 12th, I to the 16th, and so on. So I to the 13th power can be written as I times I to the 12th. Now why did I choose 12? Because I just chose the closest multiple of 4 without going over. And that is a 1. So I to the 13th is the same as I. Now there's some of these in Hawks where they ask you to simplify some power of I. There is a slightly easier way of going about this. If you want to simplify a power of I, you can simply divide that power by 4 because every cycle of 4 is 1. So 4 goes into 13 3 times. 3 times 4 is 12. You subtract, you get 1. I to the 13th is the same as I to the 1. If you just use that remainder, then that's going to be the same thing. And this remainder is going to be somewhere between 0 and 3. So you're going to get like one of these first 3 on here. So if you divide the exponent by 4, it removes those multiples of 4, and the remainder is your new exponent. So that's a nice little shortcut for these. So if you're asked to simplify I to the 58th power, you divide it by 4. All right, so we're going to, X right there. I don't know why I put that there. So we get 4 goes into 58. How many times? Well, 4 goes into 5 once. So 1 times 4 is 4. We're going to bring down that 8. 4 goes into 18 4 times. 4 times 4 is 16. Boop, we get a remainder of 2. So I to the 58 is the same as I to the second, and we know I to the second is negative 1. That means I to the 58th power can be more further simplified into just being negative 1. Now, if you wanted to do it the way that I mentioned earlier, you can, but you certainly don't have to. I just wanted to point that out. So the division by 4 is just removing the I to that multiple of 4 power and just finding the remainder for us. All right, so 68. All right, so here we go. Let's divide 68 by 4. So I ended up with 17 and a remainder of 0. I to the 0 power, that's just 1. Remember that that exponent rule that, anything non-zero to the 0 power is 1? There you go. Now, the reason it's 1 is because 68 is a multiple of 4. So we get I to the 68th power is the same thing as 1. All right, how about I to the 19th? Well, let's divide 4 into 19. It goes 4 times. So I to the 19th is the same thing as I cubed. And then I cubed is the same thing as negative I. Now, how did I get from there? I just used that chart that I made a couple of pages back here of I cubed being negative I. Because your answer is either going to be I, negative 1, negative I, or 1. That's what your answers are going to be for all of these. So that's what your answers are going to be for all these exponents. If you have I to some power, it's going to be one of those 4. Okay, last up is division. We divide complex numbers by multiplying the numerator and the denominator by the complex conjugate. This is similar to what we did when we rationalized denominators back in section 9.4. The conjugate changes the sign on the imaginary part. So we have this complex number, and then we have the conjugate. Notice that the sign on the imaginary part is what changes. So if we have to divide, I'm going to multiply the top and bottom by the conjugate of the denominator. So multiplying by the conjugate of the denominator on the top and bottom, remember that's just multiplying by 1. So here's what it's going to look like. All right, we're about to have to FOIL out the top and the bottom, so it's about to be a hot mess. So 1 times 2 is 2, 1 times 3i times 2, I times 3i. On the bottom, 2 times 2, 2 times 3i, negative 3i times 2, negative 3i times positive 3i. Everywhere there's an I squared, I'm going to replace it with negative 1. See how that blue came back in here? This is going to simplify into 2 plus 5i minus 3. Those multiply out. 4, and that's going to be a plus 9. And then we get 4 plus 9 is 13. 2 minus 3 is negative 1. You can write it like this, or you can split it into 2 fractions. Either answer is acceptable in Hawks. So either way that you want to write it. But the point is that when you divide, that you don't want any imaginary numbers in the denominator. Just like with the radicals, you didn't want any radicals in the denominator, you don't want any i's in the denominator. Okay, so let's look at another one here. I'm going to multiply by the complex conjugate, which is the conjugate of the denominator. Notice I'm only changing the middle sign. Doing some distributing here. I'm going to get negative 4 plus 20i. In the bottom, I'm going to get positive 1 minus 5i plus 5i, and then minus 25i squared. That I squared turns into a negative 1. That negative times that negative gives you a positive. And once again, you can rewrite this as 2 fractions. And I chose to rewrite it as 2 fractions this time so that I could reduce them, because 4 over 26 reduces, as does 20 over 26. If you struggle with reducing fractions, remember your calculator will reduce it for you. So if you do negative 4 over 26 and you just hit enter, it will reduce it for you. Same thing with 20 over 26, it'll reduce it for you. Six plus 3i over I. So what's the conjugate of I? Well, the conjugate changes the sign on the imaginary part. The imaginary part is that 1i. Its conjugate's negative I. So I'm going to multiply through. Now in this case, I'm going to have to distribute from right to left here instead of left to right. So I'm going to get negative 6i minus 3i squared over negative I squared. Those I squareds turn into negative 1s. That's going to be a positive 3, and that's going to be a positive 1. I don't have to write that 1. That's not necessary. So it just simplifies to be negative 6i plus 3. Or if you wanted to write it real part first, you can write the positive 3 first and then the minus 6i. Same answer. Okay, last one. Let's look at some negative powers of I. If you have a negative exponent, remember from our exponent rules that this one down here, rule number 7, that something to a negative power is 1 over that thing to a positive power. So I to the negative 2 is the same as 1 over I squared. Well, remember what I squared is equal to? I squared is equal to negative 1. So 1 divided by negative 1 is just negative 1. Let's do one that doesn't work out quite so pretty. How about I to the negative 33rd power? All right, we rewrite it as 1 over I to the 33rd power. Now, before I do anything else, let's simplify this I to the 33rd into something nicer. So let's divide it by 4 and get that remainder. So 4 goes into 33 8 times. We get a remainder of 1. That means I to the 33rd is the same as I to the 1st. Right? So we get 1 over I, or I to the 1st. I just didn't have to write that 1. Now I can rationalize it by multiplying by the conjugate. So in case you're wondering what's happening here, that's the conjugate of I. In doing so, I get negative I on the top, and I get negative I squared on the bottom. The I squared becomes negative 1. Those two negatives make a positive 1 in the bottom. So I get negative I over 1. So what we have to do is a combination of that shortcut of dividing by 4 to simplify that exponent. We have to use that exponent rule to move this negative exponent down, and we have to use that conjugate business. So there was a lot of stuff happening in what looks like just kind of an innocent little problem, right? You don't expect, this thing to turn out to be quite so much work, right? It's just, sometimes those little problems get you. It's like the little dog, right? You're like, oh, it's a cute little dog, and next thing you know, he's like ripping your face off or something. It's, because little Pomeranians are like that. Okay, so that concludes sections 9.7 and 9.8.